In my previous video, I modified the version of Microsoft Basic running on my breadboard 6502 computer to add a couple new instructions. LCD print, which sends a character code to the LCD to display text, and LCD command, which sends commands to the LCD, like to clear the screen. But to display a string, I needed to write a program like this with a loop that sends each character code separately. And I mentioned in the last video that it might be nice if you could just say LCD print with a string like this. It might even be noticeably faster. Well, that's what I'm going to do in this video. And just a quick reminder that I still sell the kits to build your own 6502 computer, including the serial interface and programmer that I use. Everything's available on my website, eater.net/6502, so check that out if you're interested. But anyway, to modify the LCD print instruction to handle a string instead of a single character code, let's take a look at the code for LCD print. You can see the first thing it does is it jumps to subroutine for get byte. And this was a subroutine that I discovered by looking through the code for poke in the previous video. And, I want to be clear, I'm by no means an expert when it comes to this Microsoft Basic code, or, even to be honest, serious assembly programming. But I'm just going to walk you through my guesswork and thought process in this video in case you might find bits of it interesting. And, I'm sure there are people out there who know this stuff, way better than I do and probably think I'm going about this all wrong, but I'm just trying to figure this out, and I thought I'd bring you along for the journey. So instead of get byte, I know we're going to need some other code here to parse a string. And the closest command that does something similar to what I want is, of course, the print instruction. And the code for that is over here in the print.s source file. So that seems like a reasonable place to start looking. And so here's where the code starts for the print statement. And print statement, of course, if I just say print hello, it prints hello. And so as I started reading through this, it's a little bit confusing because you have all these conditional defines because, again, this particular code base for Microsoft Basic can build different versions of Microsoft Basic for different platforms. So one thing to kind of simplify this is just temporarily delete the conditional compilation stuff that doesn't apply, so to make it a little bit easier to follow. But the first thing that happens, it looks like when we come into print, we have a branch if equal. So that would seem to handle some special case, maybe to do with carriage returns, not really sure. But if that doesn't branch, then this also isn't going to branch. Then it looks like we're comparing the A register with a couple different tokens, a token for a tab instruction, token for a space instruction, and jumping to different things. And this, I think, has to do with formatting. Then we compare with the comma and branch somewhere else. If it's a comma, then we check for 3b, which is a semicolon, and branch somewhere else. Otherwise, we drop down to here. So basically, all of this code here seems to be handling, kind of some special cases, which might be relevant, might not be. But for now, I'm kind of looking for the most common path through this code, which seems to put us here, jumping to this subroutine FRM EVL. And it turns out this subroutine is pretty interesting. It's defined over in eval.s. So let's take a look at that. And so here it is, and there's a comment that, in theory, says what it does. And it says, evaluate the expression at text pointer, leaving the result in FAC. Works for both string and numeric expressions. And, when I first started poking through this code, I didn't really know what any of this meant. What's text pointer? What's FAC? What even is FRM EVL? Is it form evaluate, formula evaluate, from evaluated? Still not entirely sure. I think probably formula evaluate is probably the closest to what this does. So that's what I'm going to go with. But text pointer and FAC are both defined over in zeropage.s, and that does mean something. So the zero page for the 6502 processor refers to the first 256 bytes of address space. So here's the address layout for a computer. Half of it is ROM, and this first section here is RAM. And then we've got some addresses here reserved for I/O. But the first 256 bytes from 0000 to 00FF are in RAM and are used to store frequently used variables because the 6502 processor executes instructions that read or modify data in the zero page faster than the same instruction if it's accessing data elsewhere in RAM or elsewhere in memory. So in a program for the 6502, you want to put all your most frequently accessed data into the zero page if possible. And if we look at zeropage.s from Microsoft Basic, we can see all these variables that are defined, and how many bytes are reserved for each. And you can see that includes this FAC variable, as well as towards the end down here, text pointer. But with all of the conditional compilation in this file, it's a little difficult to figure out exactly where in the zero page each of these variables, actually is going to end up in our particular computer. We could figure it out by interpreting all of the conditional compilation and so on. But an easier way for me to be sure is just to have the computer print it out. So we go back to the code for my custom LCD print instruction. I'm just going to modify this to print out the addresses of a couple zero-page variables. So I'll load A with the absolute value of FAC, and then jump subroutine to print byte. And that'll print out which byte in the zero page that FAC variable is. And then I'll do the same for text pointer. And then, in the process of figuring all of this out, there were a couple other zero page variables that were interesting as well. So I'm going to print out a couple more. Those are going to be input buffer and val type. And I'll talk more about those in a little bit. And then, after printing out all those variable addresses, I'm going to jump to address FE00, and that's the address of Wasmon. So, basically for now, to help understand how this works, I'm just going to drop into Wasmon, and then we can kind of poke around from there. So, basically, this is my new LCD print instruction for now. So I'll save that, build it, and what did I do wrong? So did I mistype that? I think what I wanted was val type without the E. Yep, that's the one. So with that new code, we'll put the ROM back in and reset. So now I'll run basic at address 8000. And now if I do LCD print hello world, it prints out those addresses and then drops to Wasmon. So I'm actually back in Wasmon. That's what the backslash indicates there. And so B8 is the address of that FAC variable. D1 is the address of text pointer. 1.2 is input buffer, and 6.6 is val type. That's what we've learned. But now that we're in Wasmon, I can print out the current state of the zero page so we can see what it actually looks like when our LCD print subroutine is called. So if I just type 00.ff, that'll print that range of addresses, and we can see what's in memory. And so what I notice is if we look at the value of text pointer, which is at address D1, so that's here, it's 14. And actually, I think it's a 2-byte value in little endian format. So the first byte is the little end. So it'd be 0014 is the address. And if we look at what's in address 0014, that's 01234, that's here. We see a 22, which is the ASCII value for a quote. And then it's followed by our string. 48 is a capital H, 65 is lowercase e, and so on until we get to another 22 right here, which is the close quote, followed by a null. So we found the string, and I guess we could just print that to the LCD, but I think we can do better because suppose it's not a string literal. So let me restart basic, and let's say we have a variable $x equal to some string. We should be able to do LCD print $x. So now if we look at text pointer again, so we look at 00.ff to look at our zero page again. Text pointer is still D1, so it's address 0014. We go back to 0014, we see capital X $. So it's literally $x. And ideally, we'd want to evaluate that and resolve it to the value of that string. So instead of being literally $x, we want to actually see the value of that string as hello. But it turns out that's actually what this formula eval subroutine does. The comment says it evaluates the expression at text pointer, which we now know is just whatever was typed after LCD print instruction, and it leaves the result in FAC, which we also now know the address of. So let's add a call to formula eval to our LCD print code before dropping into Wasmon to see what changes. So I'll add jump subroutine formula eval. We'll save that, build it, write that to the ROM. There it goes. Put the ROM back in, reset. Now if I go back into basic, I'll do the LCD print hello world again. It drops to Wasmon again, and we can look at the zero page to see what's different after calling formula eval. And text pointer is D1 again. So if we look at D1, now it's 0023. So if we look at 0023, what's there? It's a null. And that's because our string still starts at 0014 up here and then ends just before 0023. But by calling that formula eval subroutine, it's parsed the string and advanced that text pointer. In fact, one of the other zero page addresses that I was printing out up here is input buffer, and that's at address 12. And that's actually where the full command starts. If we look at address 12, that's here it's 9D, followed by a space, followed by open quote, and then our string. So it translated the LCD print command to a token, 9D, but otherwise this is the full input buffer. And text pointer is just a pointer that moves along within this buffer as we parse each piece of it. But anyway, now the result is supposed to end up in that FAC variable, which is at address B8. If we look at what's in address B8, it's not exactly obvious what's going on here. And so kind of from reading the code, it seemed to me like this variable is supposed to be 5 bytes long, this FAC variable. So this whole thing is that FAC, but still not entirely obvious what it means. But by trying some different things and kind of seeing how this changed, I was able to sort of conclude what format it looks like it's in. And so one thing that I noticed is that the first byte here, 0D, that's 13 in decimal. And indeed, this hello world string is actually 13 bytes long. So, and in fact, this does seem to indicate the length of the string. And then the next 2 bytes are a little endian address, 3FF3. And I found that interesting for a couple of reasons. One, it's at the very end of RAM, right? Because RAM runs from 000 to 3FFF. And so this is very close to the end of RAM. But then if we look at what's actually there, if we look at 3FF0 to 3FFF, what we find is that starting at 3FF3, we have HELLO, comma, space, WORLD, exclamation. So it's parsed the string and it's put it in memory. And the result here is the length of the string and then the address of the string. So that seems pretty cool. And then, the other thing that I'll note now that I, didn't notice this initially, but you'll see this becomes relevant, is that the next 2 bytes, this 0070, is actually also another address. And if we look at what's there, it's, in the 0 page, 0070, it's kind of that same thing again. It's the 13 byte, 0D, tells us how long the string is, and then 3FF3, the address of the string. And the way I was able to kind of unravel this and understand better what's going on is just by trying different experiments and seeing what the result is. So, from here, I can just hop back into BASIC. And for example, now let's try assigning a string value to a variable. Say var $ equals hello. And then if I do LCD print var $, let's take a look at the parsed version of that at address B8 to BF. And, here something seems kind of weird because if this is the length 6, that's not right because hello is 5 bytes. And then this address, if that's what it is, 8276 is how you would read this. That's in ROM. So that also doesn't make sense because, we typed this, it should be in RAM. It's not going to be in ROM. So this can't possibly be our variable. But let's look at that address. So what is it? 8276 to 827B would be those 6 bytes. And what we have is a carriage return, a line feed, a capital O, a capital K, another carriage return, another line feed. And so this kind of just looks like the basic OK prompt, right? Which doesn't seem to have anything to do with our string. I'm really not sure what to make of this. But if we keep going here, if we ignore all this, these last 2 bytes, 0405, those do point to an address in RAM. And if we look at, 0400 to 040F, 0405 starts here, and it's a 5, and then the next 2 bytes are 3FFB. And that actually is the string. It's 5 characters long, and it has a pointer to 3FFB. So if we look at 3FFB to 3FFF, here it is, HELLO. So it seems like in the case of the string literal up here, where we print hello world, we can look at these 2 bytes here, 0070, and if we go there, then we get the length of the string and an address. Same thing, if it's a variable pointing to a string, we can do the same thing. We have to look at these 4th and 5th bytes after FAC and interpret this as an address 0405. If we look at 0405, we then get a string descriptor with the length and then the address of the actual string. So either way, whether it's a string literal or a string variable, that seems to work. But then the other case is that if instead of a string, the expression is numeric, it seems like it works a little bit differently. So if I hop back into BASIC and do LCD print 1 plus 2, this should give us a 3 somewhere. But if we look at that FAC variable, so B8 to BF, we've got a completely different format. This 82 is no longer a length, of course. And this whole thing is a different format altogether. This is certainly not a pointer to to a string or anything. And so, after some trial and error with different numbers, I concluded that this is actually a representation of the number 3 in floating point format. So the C0 and then all these zeros, if you convert that to binary, you end up with 1, 1, followed by a bunch of zeros. And then this 2, actually, it turns out, tells you how many of those bits are on the left side of the decimal point, or radix point, I guess. So 2 bits are on the left side. So if you take the first 2 bits of this, you get 1, 1. And a binary of 1, 1 represents 3. So in a way, this is actually a representation of the number 3. And if that doesn't make sense, maybe I could do a separate video on floating point numbers. Let me know if that interests you. But my guess is that FAC, which is what this variable is called, actually probably stands for floating point accumulator. And again, I'm just trying to figure this out by reading the code, but that's just a guess. But when the argument here evaluates to a number, it seems like it winds up here in this sort of floating point format. So it seems like this can actually take on 2 completely different formats, whether you have a string or a number. And that's why I was also printing out the location of this val type variable. And so this is val type, it's at address 66. If we look at address 66, in this case, it's a 0. And I think that indicates that this is a number. If we look back when we were doing our strings, if we look at address 66 for a string, it's FF. So I think this val type variable tells us which type of value we have in the floating point accumulator, either a floating point number if it's 0, or a pointer to a string descriptor if it's FF. So with that in mind, let's go back to the code for the print statement. So here's where it calls formula eval. So that does the formula evaluation, which populates the FAC, the floating point accumulator, whatever you want to call it. And then it's followed immediately by a bit test of val type. And then a branch if minus to print string. So basically, if this evaluated to a string, it goes off and prints the string. Otherwise, we're going to have, it means we have a floating point number, in which case it calls f out, then strlit. And then if we ignore this conditional compilation stuff here, it does a string print. So let's copy that same logic to our LCD code. So after we evaluate the expression, we'll bit test val type, and then branch if minus set. So this will be if it's actually a string to LCD print, which will just be right here. Otherwise, we'll call those same 2 subroutines. So if we don't follow this branch to LCD print, we'll end up in here, and we'll call those subroutines. So first is f out, and then strlit. And so my guess is that these 2 function calls somehow are going to convert our floating point number into a string. But let's actually take a look at them just to see. So first, f out I found is defined in float.s. And the comment says it converts the floating point accumulator, I guess, to a string, returning with the y and a registers pointing at that string. So that seems to make sense that f out is for outputting a floating point number in string format. So it does that conversion. Then after f out, we call strlit, and this is defined in string.s. Here it is. And the comment here says that it builds a descriptor for a string starting at y comma a, and that's where f out puts its result. So we're taking what f out results. And it creates a temporary string descriptor pointed to by FAC plus 3 and FAC plus 4. So that's actually the 4th and 5th bytes of that FAC, which is, as we saw, the same as any other string. So it seems like the combination of f out and strlit will take a floating point number, convert it to a string, and then get a pointer to that string into the same position that we would have a pointer to the string descriptor for any other string. So that either way, when we end up down here at LCD print, we should end up with a string. So let's see how this works. So it's right now, when we get to LCD print, we're just going to drop out to Wasman so we can kind of see where we stand. So let me save this. We'll rebuild and write it to the ROM again. So reinstall the ROM and reset. We'll jump into BASIC and see where we stand. So if we do LCD print hello, we can look at the FAC at B8 to BF. And then these 2 bytes here, 0070, are the address of the string descriptor. So if we look at 0070 to 0072, we see we have a 5-byte string, and it's at 3FFB. So if we look at 3FFB to 3FFF, there's our string, HELLO. Now if we try again with a string variable, I'll set $$ equal to test2, and then LCD print $. And then same as before, if we look at B8 to BF, these 2 bytes here, 0405, should give us the string descriptor. So if we look at 0405 to 0407, this is our string descriptor. So now we have a 6-byte string starting at 3FFA. If we look at 3FFA to 3FFF, here's our string, TEST space 2. Now let's try a numeric expression. We'll do LCD print 6 times 7. And same as before, we'll start again at B8 through BF. And so now this is telling us the string descriptor is at 0070. So let's look at 0070 to 0072. Here's our string descriptor. It says it's 3 bytes long, and it's at 0100. So if we look at 0100 to 0102, we have a space and a 42. So it formatted 6 times 7 as 42 with a space in front. So this looks great. We've got a consistent way of taking a variety of different expressions with our LCD print instruction and getting a well-formatted string. So if we go back to the print code, not our LCD code, but the print code one last time here, at this point, it just needs to print out the string and does that by calling the stir print. But something I noticed is that if we jump down to where stir print is defined here, the first thing it does is it calls this freefac subroutine. And then, if you look at the rest of it, it looks like a fairly straightforward loop to print out, 1 character at a time here by calling this outdo for each character pointed to by index at offset y. And then y is being incremented here. But index is kind of a weird thing because we haven't seen that one before. This is sort of the first time coming across that. And then, what is this call to freefac, whatever that is? What does that do? Well, if we look at freefac, it's defined in string.s. We find that. So this says that if a string descriptor that's pointed to by FAC +3 and +4, that's what we're working with, if it's a temporary string, release it. And this seems important because, if in the course of evaluating the expression, it creates a string in memory somewhere, it's presumably or hopefully going to reserve that memory and not use it for anything else until it knows that we're done with that string. So, if we don't release the memory, then we may end up with a memory leak and eventually run out of available memory, even if we're not really using any of it. So it seems like not calling this, if we need to, could induce a pretty bad bug of a memory leak. And then the other thing is, just kind of skimming this down here, eventually it returns from subroutine somewhere down here. It seems like it returns with index and index +1 pointing at that string. And then the A register eventually starts out here before it's pushed as the length of the string. So it seems that by calling this freefac, we get the length of the string in the A register, and then we get index pointing to the string. And while presumably it's releasing that memory that index points to, the data is still there, and so we can access it at least for a moment, even if we can't rely on it being there later. And so with that, again, we can just basically kind of copy what the print routine was doing. So if I go back to our LCD code, I'll get rid of the call to wasmon and add that call to freefac. And so that's going to return with index pointing to the string and the length of the string in the A register. So then we can just loop through the string and print each character. So I'll start with y equal to 0, and then load A with index offset by y. So that'll grab the next character from the string into the A register, and then we can call a subroutine to print that character. We'll call it LCD print char to print a character, and then increment y each time through the loop. And then so to print the character, I'm calling this LCD print char, which is just going to be the rest of the code here that we had before for printing a character, because we already have that code, except that we don't need to call this get byte because we're just going to start with the byte we want to print in the A register. So this will be our LCD print char routine here. We call it with the byte we want to print in the A register, and it'll print that byte. So then to make this a loop, freefac returns with the length of the string in the A register. So let's transfer that to the X register. And then at the end here, we'll just decrement X and then branch if that's not yet 0 to LCD print loop. which will just be a label up here where we'll then load and print the next character. And then finally at the end here, we'll just return from subroutine. So this is our new LCD print, and actually we can clean up all this. We don't need to print out all of these zero-page variables anymore. But let's see if this works. So I'll save that, rebuild, write that to the ROM. Once that's done, we'll get the ROM back in the computer, reset it, and we'll launch into BASIC here. Okay, so now if we do LCD print hello world, I'll use the underscore trick for backspacing, which is how that works. Look at that, we got hello world. We can clear that. And let's try $s equal hello, and then LCD print $s. That works. And then I'll clear that again. And let's try LCD print 6 times 7. And it prints 42, as you'd expect. And I think the space in front is actually intentional for positive numbers. So if I do LCD command 168, that'll move the cursor to the second line. And now if I do LCD print -6 times 7, that prints -42. So for positive numbers, it leads with a space. For negative numbers, it prints the minus sign. So I guess the numbers line up or something. So everything seems to work as I'd expect. So I'm pretty happy with that. Hopefully you found that interesting.